Okay, for this, I'm going to go over how to use PCA, Principal Component Analysis, in Weka for you guys. So this is just about the software, not about so much the concepts involved in Principal Component Analysis or anything like that. So all of this stuff we're talking about right now has to do with numerical data. So we want a numerical data set to mess with. And I'm going to open the CPU data, which comes with Weka, and is one of the ones that's described in Chapter 1 of the textbook. So like with a few other things we've seen, we have two options where we want to select attributes. One way we can do it is through the preprocess tab, and then of course there's the whole select attribute tab. I think what I'm going to do first is I'm going to show you how to use the select attribute tab, and then I'll show you how to use the preprocess tab. Both of these may relate to stuff you're asked to do in your homework. So for principal component analysis, the first thing we need to do is we need to choose that. Right now it's doing this subset evaluator, which I believe is on the extra credit assignment. So if we select a different one, we can find principal components down here. We get a message that we need to use a different search method. We can just say yes, and it will accept it. And so right now, I'm not going to worry about the parameters for the ranker. I'll talk about those in just a second. I will talk briefly about the principal component parameters. So when I put these up here, the center data one has to do with whether it's going to use z-scores or not. When it's false, it will calculate z-scores, which is the way we defined it. So I think we always want to use false. The maximum attribute names is not really something we have to worry about. It just affects the output. So you can experiment with changing it, but you can also just leave it back the way it is and transform back to original. Once again, that's something that we can always leave it false, although mess around with it if you want to. The one I want to talk about is the variance covered. This is 0.95 or 95%. So we can use principal components to try to be approximate, or we can make it try to be exact. And so what it basically does is it changes the features around, it combines them. So thinking about the weather data, it would make a new feature that would be something like 50% humidity and 50% outlook. And so it would do an average of those two and make a new feature. So we can define how accurate we want that to be, or how much of the original interesting stuff going on in the data we want to preserve. And that shows up as the variance. And I will talk about that briefly in a little bit. So here we're preserving 95% of it. And that's a pretty high amount. Really, it's not really feasible to take this number up to 1 and expect anything magic to happen. So we can leave it like this, or we can experiment with smaller values. So we can go down to 75%, 0.75, 60%, 0.6. But that's really the only interesting parameter for us with principal component analysis. So I'm going to leave this one the way it is. I'm going to hit start, and we're going to see that we get some output. A lot of it is stuff that we really don't have to worry about. It's just too mathematical for an undergrad data mining course, but some of it relates to things that we've talked about. And so the first one, if I scroll up into the output, I see the correlation matrix. And so if we take a look at that, then this relates to the things we've been talking about with covariance and correlation. And so what we see if we look at the diagonal, all of these things are 1. And so we have what's a standard deviation of 1. So this is the hallmark of a z-score. So what this is taking the features in our data set, and it's doing something like that scatter plot matrix. So we have like the first feature, second feature, third feature, fourth, fifth, and six features in the data set. Count them if you don't believe me. And then same thing with the columns. So what this is, on the diagonal, we get the standard deviations. And so these are all z-scores, so they're going to end up being 1. If we'd experiment with that center data, we might see something different. And then in the off diagonal, we get things like, okay, this is the covariance, or excuse me, this is actually the correlation, correlation matrix. This is the correlation of feature 2 with feature 4, and it's 0.53. So they're positively correlated. If we want to say, okay, well, what about the correlation of feature 4 with feature 2? It's exactly the same thing. So this is something that would be called a symmetric matrix. We only need to look at either the upper half or the lower half. There's not new information in the 2-4 term versus the 4-2 term. So if we want to know, well, what do we get with this? We're looking for big correlations. We want features that are related to each other. And so here we see feature 2 and 3 have a correlation of 0.76. So the bigger this is, the more positively correlated. The smaller the negative numbers, the more negatively correlated it is. When we get a measure of 0, that means they're completely uncorrelated. So what principal component analysis does is it combines these things like I've already mentioned, and it makes new features that are kind of complicated combinations of the other features. So if I get back to the mouse pointer here, we can see those right here at the very bottom. And so we have a section that is called, that we're seeing as the ranked attributes, and sorry, it's a little hard to circle. And then here we see this is actually the combination of features. These are the features in our data set, and then this is telling us how much of that feature is being used. So we can read this as 47% max, 43% CH-min, and so on. These things, they're not true averages like a class score where they add up to 100. That all that normalization kind of happens after the fact. So these don't necessarily add up to anything special. And what's important, what makes principal component analysis useful is that these things are ranked. And so this has to do with how much of the variance they cover. So, and these things do add up to 1. So this is 44% of the variance, 30%, 18%. So right there we have about 93% of the variance left over. And here's the last little bit. When I said it added up to 1, I'm being a little fast and loose. It adds up to 0.95. How much of the variance did we preserve? But the thing about data sets is variance means interesting stuff. It's a chance where we have something that varies, something that changes, and then that lets us predict a class. So with a data set, variance is good. And so what we want when we're doing this stuff is from PCA, we want to get large variance. And so if we kept 3 attributes, if we just keep the top 3 ranked ones, we would get 44% plus 30% plus 18%. We add that up and we get 92% of the variance. We can also think of this, variance is kind of Greek to you guys. You can think of this as 92% of the useful information in the data set. So we threw away 40% of the features, 2 of them right here, and we still kept 92% of the information. Fewer features means simpler stuff, and so this is a good thing to do. What makes PCA useful is if we have a bigger data set with 20 features instead of just 6, we still quite often find that if we keep the top 5, we get 75, 80, or 90% of the information. And so we can throw away a lot of stuff that just makes things slower and more complicated. So this is why PCA is useful, and this is where Weka tells us that information. The other useful information we get out of this is, well, if you start thinking, well, okay, that's great, but these are different features. I don't know how they relate to the original ones. That's what we get right here. This tells us that Mmax contributes a lot to the most important feature in the data set. Likewise, CHmin contributes a lot. So this gives us the information of the relative importance of the original features right here. This is the way we think of PCA. So it's great that this ranks the attributes, but so far we haven't done anything to throw away the least useful ones. If we want to do that, we can go and mess with the parameters of the ranker, the search method that we're using here. And so when this is set to num to select as -1, that means to keep everything. So the way we want to use this, we can run principal component analysis with the defaults, and we can see what the rankings are. And then we saw that 3 features had most of what we needed, and so we want to keep 3. So then we can run it again and change num to select to 3. And then when we do that and we start, we end up with just 3 attributes left. So now we've actually changed our data set. We've taken it down from a 6-attribute data set to a 3-attribute data set, which is kind of a nice thing to be able to do. So at this point, if we want to use those attributes, we need to save the model in the Select Attribute tab. What I want to do now to try to keep this moving fast is switch gears and go back to the Pre-Process tab. And we want to see how to do something similar in the Pre-Process tab. If we know which features, how many features we want to keep, then selecting attributes is the way to go. But a lot of times we have a different threshold in mind. We don't know we want to keep 3, 4, or 5 features, but instead we know that we want to keep like up to 33% of the information saved. We have kind of a different measure for things. And so if we want to see how to do that, we can work in the Pre-Process tab. We're going to have to use Principal Components as a filter. That doesn't use anything about the class, so it's in the unsupervised folder. And then we can scroll down here and find it under Attribute, not under Instance. So we can select it. We see the same parameters that we saw before. And we can apply it. And so we get the same features that we saw before, except now we have them in the Pre-Process tab. If we look at these and compare to what we saw in Select Attributes, the features are ranked. So this is the best feature according to Principal Components Analysis. It captures most of the variance. This one captures the second most, and so on. The way that's reflected, the way the ranking is reflected in the Pre-Process tab, aside from the feature number, is that we can look over here and we can actually see the variance of this new feature. So it's 1.8 for the first one, 0.9 for the second one, so it went down by 50%, 0.86, 0.705, 0.636. So the variance gets less and less. And so if we want to think, well, how can we actually figure out that having a big variance, it means something useful in data mining? Think about if a feature, or in this case a combination of features, has 0 variance. What that means is they don't change at all. So that's like a constant feature. It always has the same value. In a classification problem, if we have 2 classes that are 100 instances are split between, but then we have a feature that always has the same value, that feature is useless for classification. When the feature varies, when it changes a lot, then we have the ability to use 1R, build decision trees, or k-nearest neighbors, or clustering or anything. It becomes useful. So the trend that we're dealing with, and kind of the whole point of this last part of the course, is that having variance is useful. So it's the way that we want to decide if a combination of features is good or bad in PCA. So if we're using the Pre-Process tab, and we know that the variance of the first one, the one that varies the most, is 1.832, we can kind of think of that as our maximum variance. And then we can think of a threshold where we only want to keep features that have, say, 50% of that variance. So we can use a threshold of 0.5. So if we do that, if we take this thing, multiply it by 0.5 or divide it by 2, then we end up with 0.916 in this case. So then what we do is we only want to keep features whose variance is above the threshold. That's the way we use PCA in this scheme. And oops, I made something happen I didn't want to. So keep features, and these are new features from PCA, the combinations, not the original one. So we want to keep features whose variance is greater than the max variance, so that's the variance of feature 1, times the threshold. And this is something that you guys are asked to do on the homework. So this is our cutoff value. All the features whose variance is above 0.916 we would keep with a 50% threshold. And so all we have to do, we know the first one's going to make the cut. As long as our threshold is 1 or less, the first one's always going to make the cut. We look at the second one, 0.911. It's actually less than our threshold. So then we can say, okay, we're going to get rid of all the other features. And so we actually end up with just a single feature set, and then I can remove these and they're gone. So that's how we use a threshold of 50%. When we looked at PCA, we saw that actually that the first three features were the best. So if I undo this, or if I data mine and find that I'm not getting very good results, I would go back and I would start over with the transform features, keeping all of them, and then I would consider a different threshold. So let's say in that case, we're going to change the threshold to 0.25. So then that's 25% divided by 4. So what we had last time was 916. So now we're half of that again. And so that's something about like 0.455, something like that. So we do what we did before. We know we're going to keep the first feature because it's got the most variance. We look at the second one. It's variance 0.911. That's above the threshold, so we keep it. 0.86, that's above the threshold, so we're going to keep it. 0.7, it's above the threshold. 0.636. All of these are above the threshold in this case. So now we lowered it and we kept everything. So somewhere between 0.25 and 0.5, there's a threshold that may be a little bit more useful where we can get rid of, say, feature 4 and feature 5. So at this point, we're just iterating. So let's consider a threshold of 0.4. And dividing won't necessarily help me anymore, so now I'm going to take the maximum variance and I'm going to multiply it by 0.4, and that's going to give me, if I divide this by 10, I get 0.18 multiplied by 0.4, so I get 0.72 for my cutoff in this case. So same thing, we look at the first feature, it's going to be above it. By definition, we know that. Second one, 0.911, bigger than 0.72, so we're going to keep it. 0.86, bigger than 0.72. Oh, this one is below the threshold, so we're going to remove it. And we don't even have to check for 5 because these things are sorted in descending order. It's below the threshold as well. So then we can remove those attributes. We've ended up with a 3 attribute data set. So these are the two ways we can use PCA. We can use the preprocess tab, and we can look at the standard deviations, and we can remove attributes as needed with the threshold. Or we can use select attributes, and we can specify how many attributes we want to keep. When we do that approach, we need to run PCA and keep all the attributes first, look at the output, get a sense for how the variance goes to decide how many are important.